Hello, everyone.
Hello,
Today we have cosmology topic and a few questions. I've put the file with the questions in chat, just in case if someone needs it. And so I will be. We have 2 hours. And I will be reading questions, then Vitaly answers, and then we can discuss and ask more questions. So let's start. The first question is, what is the nature of fundamental time? Fundamental, I mean, versus computational. And but is it really fundamental?
Right. So in physics, time has different meanings depending of what branch of physics you study. So there is a well-defined time in quantum mechanics. We know what it is. It's a certain coordinate. We know how to handle it. Then there is a different time, time in general relativity. Now, the general relativity time is more tricky, because different observers in space-time may sense and measure time differently, right? So the well-known twin paradox or time dilation phenomena tells us there is no such thing as a universal time when you are dealing with the gravitational system. There is for quantum mechanics, but there isn't for general relativity. And so when you try to ask the question about what is the fundamental time in context of the learning systems, then the answer is already there, right? For the learning system, it is the computational time. It is the computational time which is clicking and which kind of measures the computations that you do. In context of the learning systems, it's the learning computation that you do. So now, how is this related to the 2 times that I just mentioned earlier? So basically, the idea is that computational time is closely related to quantum mechanics time. And so when the system is, and it actually plays the same role if you study how the quantum mechanics emerges from it. But for the general relativity time, it is not a fundamental, it's more of an emergent sense in which, and so in that context, it is okay for other different observers to observe different flow of time. So this is at least how we understood it. Now, the one more thing I'll probably want to add to this is that there is widespread study about what the role of time is and the error of time, and many people try to connect it to the second law of thermodynamics, meaning we observe the flow of time in the direction where entropy grows, right? So it's a entropic time. So it's the third one. So in physics, then there's quantum mechanical time, there is time associated with general relativity, and then there's thermodynamic time of how entropy grows. Now, of course, this isn't the whole story, because in learning system, we know that the 2 effects happen. Entropy grows due to activation dynamics if there is not much learning happening. And also entropy can decay if the system is learning the environment, right? And so, and then now it becomes possible for you to actually have different notions of this entropic time, because depending on how much you learn versus how much you forget, the time may be different. So you may have some system that doesn't learn at all, and then you may say for that, or nor forget, right? Very small, tiny system, it's kind of isolated. Then you can say that for that time, there's no flow of time. But you can also have the larger systems for which both effects happen. And if the flow of time is dominated by entropy, by forgetting by entropy production, then you're mostly moving in this positive direction of the increase of the entropy. And that is why you mostly see the second law of thermodynamics to be satisfied. However, there is this additional ingredient, as I said, learning that may mix things around and make the opposite effect. The one more thing I would want to probably add to this discussion, which is also interesting, is that most of the physical laws are time symmetric. So you see that there is no asymmetry. And that's like an open question, right? So physics tells us that the evolution laws have to be symmetric to the future and the past. Somehow we see this disagreement between flow of time towards the future versus towards the past. So we do see that the second law of thermodynamics mostly works. And also we don't remember the future, we only remember the past. So there is this asymmetry between the two time directions, which is in contradictions to the usual view of physics. So that is something that in the learning dynamics tells us that, yes, if we are observing forward evolution in time, then there is trainable variables that try to decrease the entropy. There is non-trainable variables that try to increase the entropy. But if you reverse your time and kind of try to go backwards, then those two types of variables kind of switch their roles. And the ones that try to create the entropy starts destroying the entropy, and the one that tried to destroy the entropy is creating the entropy. It's not clear how the universe would look if we actually run it backwards in time all the way, but at least this is how it looks. So many subtle points there. So first, let me summarize different definitions of time, right? Quantum mechanics, general relativity, thermodynamic, and then we're trying to connect it to the computational time, fundamental computation time, if the universe is a learning system. And so we want to show how all three can arise. And the other one is this symmetry of laws, where the system seems to be symmetric to the future and to the past, at least when you observe it on the smaller scales, right? So for the gravitational scales, there are different things you have to consider for cosmological evolution, because it seems to be, it's not very symmetric to the future and to the past. But at least all of the experiments we do in the lab, they do show this past-future symmetry. Okay, so let's see if there are questions, and I'll try to answer, or maybe things that I would want to clarify. It's a complicated subject, complex subject, but let's see if we can.
I can start with a question.
Yes.
I do not quite understand about this quantum theory time, as well as I understand cosmological time, general relativity time, and thermodynamical time have one important thing in common. They are dependent on the observer. In some sense, it is defined in relative to some observant, and so we can probably understand them as emerging phenomena based on the basic computational time of the neural network, global neural network. And we can see that probably for different observers, some cosmological time appears, and some thermodynamic time appears in processes which they are part of, or which they can observe. What about quantum mechanics? What's the time there? I do not quite.
Yeah, I think it's actually easier. So the quantum mechanical time is the computational time, so they're just equal. The two it is just the same thing, right? So you're using you're writing your equations as in terms of the computational time of your neural network, and this is the very same time that shows up in the Schrodinger equation, quantum mechanics that describes evolution. Actually, the hardest one is out of all of those is the other two that you thought were easy. It is actually the general relativity time, because it depends on the observer. And remember, our neural network is defined for everything. Observer, there's no such thing as an observer, right? Every part of this network observes the other part of the network. So you cannot say, okay, this is an observer. Everything is an observer in this case. However, if you define some small subsystems that move and interact with the environment, then there is a sense in which this small subsystems receives information, which this subsystem learns this information. This is like eternal clock of the subsystems of how it is capable of receiving information or processing it. For example, if you close the subsystem and it doesn't interact with the environment and doesn't learn anything, you can then there is no notion of flow of time for it, right? So that's what I said, that if you close the system, it's not interacting, it is completely isolated, it learned anything it could, it acquired its local learning equilibrium, so there is no time to it. No time is flowing in this context.
However, once it is in equilibrium, yes, if all the internal recursive processes stopped, then there are no internal time. Yes.
However, the computational time would still run, right? So computational time would still run because it will still try to, implement this activation dynamics. So it will be a trivial dynamics. It will just be doing some useless repeated computations that are not leading to any destruction or production of entropy. It's in the equilibrium. So from that time, the computational time, fundamental time, the quantum time is running. Okay, but the other two times are not running because entropy remains constant, so entropy is not changing, and there is no interactions with the environment, and so.
But this equilibrium cycle can be quite long, and some fluctuations, some beings which appear in the process, they can live their whole life inside of this and feel their personal time. And but globally, if it's equilibrium, if there is no learning dynamics. Globally, some outside observer will see that the system is in a cycle, and
yeah. So for the okay, very good. So we have a small subsystem that reached equilibrium. Then we look at it from the outside. What do we see? We see a system that in an equilibrium state, and it's actually in a pure quantum state, and it just goes over some states and keeps going like recycling through the same states. So for the outside observer, looks like a quantum mechanical system that just stays in some pure state. Now for the but if you're asking what is the time that is measured by that system, there is no entropy growth. So that system itself wouldn't see any entropy growth, wouldn't acquire any information from the environment because it's completely isolated, closed. And so in this case, this is like an extreme case where the system itself, if we call it an observer, then there is no flow of time. Now, if we observe it, then there is a flow of computation.
No, but and also if there are some fluctuation inside of this system, the cycle can be very long, and in this cycle, some sentient beings can appear, and globally.
Oh yeah, of course, yeah. Okay, very good. So that brings us to the point of the Boltzmann brains, right? So we can have a closed system. It goes through the cycle, and then very long cycle. So classically, it's take exponentially amount of time to go through this. Now, the quantum mechanically, it will take you double exponential amount of time to go through all of the states. But once in a while, in that closed region, there are some brains will appear that will be able to process information. And so for them, and they will be quickly destroyed, right? But all this represents that equilibrium state. And then if you ask what is the flow of time for this entire system, then from the outside, it looks like they're doing some repeated.
This is really what we already discussed when we discussed what will be when all the universe becomes the single system which had learned everything and there is no outside of system. It's the same question. Yeah. And
with one correction is that would only be possible. Well, first of all, two corrections. First of all, it will only be possible in the double exponentially large amount of time, so it's very long time. The second correction, it may not be possible at all if the number of degrees of freedom is infinite. So if you have infinite network, then that's no go. And so, my bet would be that most probably this is the case, because having any finite number, if you have a finite number, you need to explain where it came from, why this number and not But in infinity is kind of zero and infinity, those two things you don't need to explain. They're kind of already there in mathematics. And moreover, if there was a finite number, most likely we would be able to observe it somehow, one way or another, if you wait long enough, in principle. So, but that's a good example of when the time, and then I would say that if the universe is finite, and if you get to this equilibrium, then I would say that eventually for that entire universe in equilibrium, just time, general relativity's time or entropic time stops. But quantum mechanical time, the time that just is the same as a computational time, will go on. It will go on, but it will be going in the very trivial directions, because you kind of always, it's completely predictable. Knowing the state of the system at one time, you can completely determine what would be in the next time. There is no, it's a completely pure state, like we call quantum mechanics, and the evolutions are would be completely predetermined. At least in the limit of when quantum mechanics is correct. Now, of course, quantum mechanical limit is not precise in this model, and so there can be fluctuations from that, and then all of a sudden the system that seems like it's in equilibrium, it gets out of the equilibrium, and then it shows not quantum behavior, and then you would be able to observe that. So then we are really saying that there are kind of three limits. One limit is when everything is equilibrated and the time is just computational time. The other limit where nothing is equilibrated and we're just looking at a small system, how it's interacts with the environment, and then time is basically, you know, by how much entropy flows into the system. And then something in between where neither of the two limits are correct, or it can be combinations of two. When and that in this case you would have to think about this as actually a learning system, and then
the question is how can we, being inside of the system, can distinguish between these two types of behavior? Probably
right. So those two times, we're not distinguishing them. We're just saying that they are correct descriptions of our subsystems in certain limit. So you take your subsystem, you start doing experiments with it. It shows you that it's a quantum state that's evolving. Like this description is correct. So you're saying, okay, well, now the more appropriate description, still approximate, but more appropriate, is quantum mechanical. And so you do your calculations quantum mechanical. Then you do other tests and you figure out, well, actually, it's not quite true. There is always kind of flow of information and it's still interacting, which has actually happened. Creating a quantum system that is isolated is very hard. This is one of the problems why quantum computers are not easy to build. Because particles try to interact with the environment. They try to get entangled with them, right? They try to talk to the environment. And for that reason, we cannot really create a completely isolated system. But if we could, we would say, okay, this mathematical apparatus is the right one to describe the evolution. Now, you can say, okay, but what if it's not right? If the system open, then there is a way for you to do it. If it's a little bit open, that there are certain like perturbative approaches where you can study the evolution where there's still some flow of entropy. But if it is completely, if it's interacting with the environment and this interaction is dominating, then you are really in the realm of thermodynamics, and your description, quantum description, isn't just correct. And then you have to either use the rules of the thermodynamics of how things flow, and in certain limit, the claim is that this thermodynamics gives emergence to the equations of general relativity. And so then that is your limit, and that is where you are studying, can use equation of general relativity to study it. But in all limits, the correct way, of course, is to write down your neural network, set it up, the evolution, and study it. And we only go to one limit or the other because it simplifies calculations, either analytical or numerical. The one more thing, yeah, okay. Any other questions, maybe before follow-up questions? Yes.
Yeah, probably. Just to clarify some questions for myself, because really the questions of nature of time is very interesting. What do you think if you take in general terms? So time is not something that exists itself, but it's time. It's an attribute of some object or environment. So we can talk about the time only in case if we can describe some system, for no matter how. And we can say that this system may change. So we may get two different descriptions of different states of some environment. And so in this case, time in general case, it's a fact that some environment may change, and time itself, it's a number of changes of some environment. And so if we have a space of different states of some environment, and so we may bring the order to this set. So one environment, some state appears after another, you may get a graph of different states, and so local path, it will be the kind of arrow of time. And so in general case, the measure of time is the number of changes. So when we're talking about the time, we mean that something may change and we may describe this change. So in this case, the time depends on the zoom, on the scale, how we describe the system. Because if we skip some details, so we may say that nothing changed in the system state, it's so time is freeze or something like this. What do you think about such points?
So first of all, graph is great, but the arrow of time is stronger than just graph. It is a directed graph where direction goes with no loops, right? So it all goes in one direction. So it's not just any graph. It's a graph where there's arrow of time, right? Not the graph of time. That's one comment. The other comment is, of course, environment plays a key role. But the interesting part with quantum mechanics, or in this language of isolated system, that you can have completely isolated system, right? No environment interacting with it. You do some measurement on it before, okay? Then you leave it isolated, and then go outside, have a coffee or whatever you want to do, come back. It was still isolated, okay? And you do a measurement. And depending how long you were outside, how long you were not interacting with the system, the outcome will change. So it seems that without environment, this system, the evolution, the time was still flowing in this system. Some kind of time was still flowing, even if there were no environment, nothing, no interaction with it. And that is quantum mechanical time. And that is why I'm saying that even if there is no change in the environment, it seems as the system is still performing some, useless computations and just evolves in some way.
So, sorry. In this experiment, do you mean that it's possible to make the second measurement when the system is exactly in the same state?
It's not in the same state. So it basically, it still evolves. If it was in the same energy eigenstate, then it doesn't matter how long you wait, you would always get the same outcome of the measurements. But if it was in some state, which is not the energy eigenstate, technical term, superposition of energy eigenstate, but so if it was in generic state, and then depending on how long time passed between the two measurements, you'll get a different outcomes. And you can really you can calculate exactly what the outcomes will be depending on how long you wait. So it means that during this waiting period, although no interaction with the environment was, something was still changing in that system. So that's kind of
another moment why I'm trying to link between states and time, because if you're talking about the quantum system, yes, you're right that if we measure, we destroy the quantum state. But if you have some quantum system and function, we describe all possible states for this function, we mean that all these possible states exist at the same time. Yes, so they are in superposition. So we mean that we don't know which state will be next, but we assume that all these states exist at the same time.
Yeah. And so I think there's So let me remove a mystery from quantum mechanics, because there is a mystery of quantum mechanics that is not necessary. We have it all the time in just improbability theory. So if you have a black box and I told you that I put there an apple, and it's this apple is either red or green, but I don't tell you which it is. Okay, this is a kind of a superposition state, right? You know there is an apple. You know if you open, you will see an apple, but you don't know what color it's going to be. Okay, so now in this example, the color of the apple will not change if you wait long enough. But what I'm saying that what potentially in quantum mechanics happens is that the color keep changing, like from red to green to back and forth, right? And then depending on when you open, you can kind of guarantee that you will see a green apple, or you are guarantee and then you will see a red apple. Because of the dynamics that happens there. But let me, before I ask for more follow-up questions, let me just say that all the constructions that we do in physics fall in the framework of dynamical systems, meaning there is a state and there is a law how the state changes. Okay. Now mathematicians study general dynamical systems. You know, you tell me what the state of space is and tell me how each state spaces, and I'll derive some conclusions. In physics, we prefer some particular dynamical systems. So one dynamical systems is quantum mechanics, where the state is actually think about distribution, probability distribution of the different states, and that evolves, or wave function, which of course has more into it than just probability distribution. In classical mechanics, it's called a phase space, and then the evolution laws are called Hamiltonian evolution laws. But again, idea is the same. There is some state, and there is some evolution, and all other branches of physics are not different. The only difference that comes with the learning dynamics is that your state space has kind of two types of states, or two types of variables: trainable and non-trainable, like the dummy ones that just go with the flow, and the smart ones that are trying to adjust and minimize entropy or minimize the loss function. And they have two types of dynamics: the stupid one, which is activation dynamics, and the smart one, which is the learning dynamics. That's the only difference. But other than that, all of those frameworks are just dynamical systems. The question is, what's the right dynamical system? And by the way, if you already say it's a dynamical system, you already assume that there is a fundamental computational time, right? Because the dynamical system changes in that time. And then all other times may just emerge through some limit. Like, for example, as we discussed, there is this notion of entropic time, right? Where time is considered flown when entropy is increased. But when entropy reached its maximum, there is no flow of time. There is, like, you know, heat death, right? So, and there is no flow of time at this point because system reached equilibrium in that definition. However, the computational time is still keeps going because there is still some evolution to the dynamical laws.
So not depends on definition of time. Time means then something may change.
Right. So in the fundamental level, it's the state that changes. So it's like we know exactly what it is on the fundamental level because there's like this is the only game in time, right? So it's the state, and the state changes. Right?
Yeah.
Now, however, we as a big objects perceive time differently. So you can like measure your biological time, or you can measure the quantum mechanical time, and this time the answers may be different. So the time that you measure in the lab as a local time may different from your time if you go ride on a bike and then come back, right? Because you've been traveling, or if you are close to a massive star, then your clock will run very fast. You know, everybody's seen the Interstellar movie, right? You spent a few hours, few minutes next to a massive star, or maybe black hole, and then all of a sudden you come back and you are still young, and everybody is already dead, right? Everybody you knew. So that is a general relativity time, because it's not a computational time, and it's not a fundamental time. It's the time that you perceive as a biological organism of a size, certain size. Okay, other questions and follow-up comments? I don't know, Alexandra, if I answered your question. I did answer something.
You added. Thank you so much.
But I gotta say that this time is a very confusing subject, right? The way I'm trying to unconfuse it is to say like everything is just dynamical system. Now tell me what your dynamical system is. So there is time, and then try to relate that time to whatever time you observed really in the lab, whether it's a quantum mechanical lab, a small lab, or it's a cosmological scale, or the twins traveling in rockets. Those times may be different. They may not be what you perceive as a fundamental time. Okay, Katya, how are we doing on time?
I think if there are, we can move to the next question. It seems like we are done with time.
So we have time to not talk about time now, right? And talk about something else. Yes. Okay.
So the next question is, what is the loss function of the universe?
Right. Yeah, that's a difficult one. Now there is one conjecture that was put forward that the loss function of the entire universe is related to learning, right? So every part of the universe tries to learn the other part of the universe. Now, if this entire entire universe was so okay, there are two choices: whether it is a supervised learning or unsupervised learning. So maybe we should start with that, and then we'll define a loss function. So supervised learning, and so there is a supervisor, okay, who is telling us what kind of computations we should be doing and what kind of things we should be trying to optimize. And then the supervisor has certain degrees of freedom that interacts with us. And for this degrees of freedom, he tells us what they should be, right? So now, if there is such a supervisor, then some of the dynamics inside in the bulk would be our own, because we may have our local loss function trying to minimize for example, the variance of the local state or the flow of information, something local defined loss function. But then there will be also a global loss function for which we'll try to minimize. So now this is one possibility. Then there is a supervisor. You should think about this as like sitting at the boundaries, and then there is a bulk where we reside, and then the loss function can be defined both on the boundary and on the bulk. That's one possibility. The other possibility is then there is no boundary, and so there is no supervisor. It's completely unsupervised learning, and we are just trying to process data inside of this universe and trying to optimize certain quantities. So what kind of quantities can they be? What can we be? So for example, the flow of information, right? So you may say each microscopic neuron tries to increase the amount of information that it carries about the rest of the universe, right? So now being in a state where no information flows through the neuron is not preferred with this respect, because basically this neuron then would not be optimizing, and the amount of information would be zero. Also, for this neuron to be connected to all other neurons is also not a good idea, because this will create too much entropy and you would not be able to learn any. It will just be, again, random. There's infinitely many neurons or large number of neurons. You get information from all of them. Basically, you will not be able to interpret it in any way. So it will, again, contain zero amount of information. So the balance is in between. So you want to process information about the universe, but you don't want to start with connecting to everyone, nor to disconnecting from everyone. So you'll have to find a balance. And then neurons, the one thing they can try to do is to form low dimensional connections. We kind of talked about this, maybe chains of neurons. And then like neuron is not connected to everyone, but connecting to a couple of neighbors or few neighbors. And then this way, there will already be a non-zero amount of information that they can process and record. Like, for example, it can record like mean value of the states of other neurons, can record locally. and then processes. And then eventually more and more complicated connections can form, and more, and by forming collaborations about those neurons, they kind of can process more and more information. So basically, to summarize, there are two possibilities: supervised, non-supervised. In the supervised, we can have both global goal, that is somebody is imposing on us, this the supervisor, and local goal, that we are just deciding that would benefit, local degrees of freedom. I say we, but of course I mean those fundamental neurons or any subsystem of this network. So that's one possibility. And then in the second possibility, if you say, no, there is no supervisor, it is just local dynamics, it's okay as well. But then you have to come up with a quantity of a local loss function. So something that's related to information. So what do I want from local neurons is to process more information, to memorize more information, to learn more information. And in this case, the argument is that neither having zero connections to other or having infinitely many connections, both of those extreme cases are not working. And so it has to be something in between. And that seems to be what we are getting. We have kind of low dimensional space of connections. And that is not too large, so that we do not get just chaotic signal, nor too small, so that we do get something. I don't know if I answered some of all questions, but I will take follow-up questions now.
Can we start from supervised learning? I do not quite understand how can it happen. Supervised learning can exist in various formats. If we talk about artificial neural networks, it can be just a data set or with some markup, which just says which answers are correct and which are not. And but also like something like reinforcement learning also falls under your definition of existence of the supervisor. But I believe that in your generic model, reinforcement learning is kind of unsupervised or not.
You can do both. You can do both. For the reinforcement learning, you can define a local loss function so that it would be unsupervised, or you don't define a local loss function. You just have somebody who tells you what's right, what's wrong. Basically, think about there is some superpower that is connected to some neurons and always tells them, oh, no, you are in the wrong state. You have to be in this state, or you have to be in that state. And I'm putting them in the boundary, but of course they can be anywhere. Boundaries is kind of in quotation marks. And then this supervisor would perturb evolution that would happen without the supervisor. It would constantly enforce something, yeah, you are maybe okay without me as supervisor. You can probably be doing your computations, but maybe I want to use you for something, right? So I want to use your resources to I don't know, solve Poincare conjecture, and then he would, that supervisor would be changing states of certain neurons, adjusting the state or adjusting the connections to those states. Basically, when he sees that there's correct, proper results that obtained, then no corrections is happening. When he sees that it's not what he wants, I don't know why I say he, but whatever. Then there some adjustment happens. So that that updates from the outside. The supervising requires us to do two things. First of all, is to define a subset of neurons which are directly being supervised, so where the direct connections changes occur and where this loss function is defined. And secondly, we have to model the dynamics of those neurons of supervision. Basically, what is the training data set that is training this entire universe? It looks as an ugly construction, because why would you want to do that? Why would you, if you can define everything without a supervisor, then you don't need it, right? Then
what I see in this is that probably if we as a learning system are part of something bigger, which is learning system, it will be indistinguishable for us from such supervisor. So it is not really a question. Yes, if we believe that at many scales above us, something, the system is learning, then we can be 100% sure that this super system acts as a supervisor on us. No question about that. So like
okay, so maybe the point is that we can take like all of the observable universe and all of the neurons that are present in our three-dimensional space and call it our universe, and then everything else we'll call the environment, and that environment will be kind of teaching the observed or three-dimensional space of how to behave.
Yes, the real question is only at the highest scale, highest imaginable scale. For on all the scales below it, the system of the next scale is behaving as a supervisor for our systems. It's not no wonder it does these things, and we cannot do about anything about it. So,
exactly.
So really, the real question is on the highest imaginable scale. Probably it is unanswerable.
Yeah, but not the length scale, because you can also have shorter distance supervision. So I can imagine that the supervisor doesn't like how the microscopic particle of a certain type behaves and keeps changing. So let's say the proton keeps decaying, right? If we just leave it alone, and that's not good. Then the rest of us would not be able to perform calculations we are doing now. So and that supervisor just keeps correcting the proton, don't decay, don't decay, don't decay. And so like some additional supervision that's needed so that the rest of the network can perform useful computation. So I can imagine this can happen on any scales. At this point, I don't think it's a complication to the system, right?
Yeah, so, you can read Strugatsky, Million Years to the End of the World, and it answers basically these questions.
What's the answer?
It's yes, homeostatic universe. It is called by Strugatsky. Is this global supervisor, which probably is not sentient, but how it behaves, they tried to imagine it. One interesting question is what if we at the on the other side, at the lowest possible level, at the level of fundamental neurons, look at the loss function. Can it behave in the same way? Can it influence in the same way our behavior at the highest scale? Can we say that something in this fundamental loss function is directing our learning, our neurons in our brain?
But everything, I think this the microscopic loss function defining fundamental neurons is the fundamental one. Everything else is emergent, right?
Yes.
So the fundamental neurons decided we want to process information, and then one poor neuron kept processing information, and he could remember a couple of bits of information. That's it, in bias and a weight. Okay, and then he decided, no, maybe I can do more than that if I start collaborating with someone, and we'll be saying, let's not record the same information, but we, together with some other neuron, I'll be recording orthogonal information to each other. And then we can now all of a sudden record twice as much information. And then more and more complex systems formed,
yes, but can we, if we say that, let's assume this is really the loss function for the fundamental neurons, can then we say that we as human beings have supervised or unsupervised or at any other scale, then all the learning is influenced by this fundamental loss function?
Yeah, but that's not supervised. But that's not, I wouldn't call it supervised, it's emergent, right? So now we are not being supervised, we are just doing exactly what the fundamental neurons wanted to do, but more efficiently. That's it. Okay, and so there's no supervision in this case. Now, of course, we can try to do the other thing is to coarse grain it from below and try to model the dynamics of us as a macroscopic neurons. And then we would effectively, to describe the system, would have to introduce some kind of effective loss function and effective supervision, so it behaves correctly. But we don't need to do that. Just on the fundamental level, there's just fundamental loss function, and everything else emerges. And
okay,
so
but then we just can look around and see that, I don't know, as a human beings, we are we use supervised learning. As a biological species, evolution is unsupervised learning. So it really means then that everything is coexisting at different scales, in different places. All the types are coexisting, probably this fundamental loss function allows for many other types of learning.
Right, but whether you call it supervised or unsupervised, it's really only an interesting question when you take the entire universe. So when you take any subsystem, of course it's supervised, because any subsystem is supervised by the environment, right? So then it's not an interesting question. The really interesting one, if we take the entire system, the entire universe, and somehow we conclude that that it became supervised. But that's again, maybe if we include the supervisor, then the whole system again becomes unsupervised, and then we are done with that, and then everything is actually unsupervised. And then the tricky part, which is kind of something we are working on right now, is to see what is really their fundamental loss function. So I already mentioned the flow of information because I know it's becomes relevant. What is the fundamental loss function, actually equation for it, that gives rise to fundamental particles, to fundamental fields, and other things, to the behavior of agents as we observe. So one example was with those self-driving cars, right? If we impose them certain terms in the loss function, then they start bouncing around and behave some kind of particles. But can we understand what kind of loss function must be imposed on them, on the agents, so that they start behaving as water molecules, or they start behaving as carbon atoms, and that is
what?
Carbon atoms or water molecules.
Specific types of molecules.
Specific. Can you really write a dual description of the physical system? So we know how to write a Hamiltonian described as a physical system, but can we now turn things around and say, okay, well, I want to understand how they behave at the level of the loss function, okay? And if I understand that, then I can keep going further and say, all right, so I understood what is the loss function that describes the dynamics of, say, water molecules. Now, can I break it further? And what is the loss function that describes the evolution of electrons, or protons, quarks, and then maybe go to the actual, fundamental units, maybe fundamental neurons, and then they will say, there it is. And it may be this. The answer may be as simple as I said. All that new fundamental neuron wants to do is process information. The more, the merrier. And that's it. And then we would be kind of everything else emerges just from this simple desire for the neurons to process information. But that is the direction to go. Of course, you just cannot just postulate everything is learning. You have to show that there is this mapping. You can take a Hamiltonian system, molecular system, and describe it in terms of loss function.
But I'm not sure I understand. You are saying that loss function, fundamental loss function of fundamental neurons is related to processing information.
Well, it's just a guess. That's a guess. It's not a proof, right? Because if I know that if I demand that neuron processes more information, then I know it will not be beneficial for the neuron to be disconnected, because then it processes zero information, and also would not be beneficial to connect to all neurons simultaneously, because it will again give you some noise, some averaged value that has no use. But if it is kind of first start with the with one connection, and then kind of understands it, and then forms collaborations with other neurons and tries to progress more information. Then there is more and more advanced information about their environment now will be stored. And so at the end of the day, with this scenario, by starting with a very simple assumption that just learn more about your environment, right? Fundamental. Each of the fundamental neurons has the same loss function. Then there are more and more complicated things would emerge, right? Just from the flow of information, from as simple as that.
Sounds like maximizing the amount of information.
Yeah,
but
knowledge.
What is the metrics of the amount of information?
So it is like negative of entropy, right? So when you, so for example, if you have a coin, right, heads on tails. Now, if you don't know which whether it's heads or tails, and it's a fair coin, you can say, well, zero amount of information if it's 50-50. So I don't know whether it's heads or tails. Let's say your entire environment is just one coin. Say the heads or tails, it's just one bit of information, right? And then you want to learn what it is. And if you know nothing about this, you have least amount of information. And so your model of the environment is it's the heads or tails. Now, let's say you looked at the coin and you discovered that it is heads, right? Now, all of a sudden, you obtain maximum amount of information about that environment. Now you know everything about the environment. So it's a one bit of information you obtain, but it can be also everything in between. You kind of know it's you've seen that it is heads, but then you also know that once in a while it flips, right? Maybe with once every year it flips, and so on average once every year, and then they ask you, okay, what is it, heads or tails? They ask you one day later and say, well, it heads, because most likely it didn't flip. Now, is it completely true? No, it might have flipped as well, but this is your best estimate of what the environment is. And so your information about the environment is still pretty high. It's very close to one bit. But eventually,
that's really the question I wanted to ask. So as well as I understand, you are saying that building models, good models which predict future, are really emerging property of this loss function. So that
that's exactly what neurons do, right? So one neuron cannot predict much of the future for the environment, right? The two neurons can do it better.
No, but the basic idea of prediction of models, it's a derivative of this intent to learn anything, everything.
Exactly. And minimize the uncertainty about the environment. So that's why I'm saying information, right? So you can phrase it different ways: minimize uncertainty about the environment, process more information about the environment, and this is the same thing.
But uncertainty itself appears out of the activation dynamics.
That's
globally,
right.
Uncertainty is only because everything is moving, and everything is moving because everything is activations go.
Exactly. But one neuron cannot model a billion of other neurons. And so potentially, if it was not one neuron, if it was a billion neuron, they can try to model the other billion neurons, right? But one neuron cannot do that. And so it has to choose what information to remember and which information to...
Then again, it's a classical theological question. What started the movement? Why they started changing in the very beginning? Really?
No, but that, okay, very good. That's a different question. So what started the two different types of dynamics: activation dynamics and the learning dynamics. Okay, now in here the approach is that you do not ask the question of what defines the dynamics, right? You're saying, I postulate the dynamics, so it's the learning dynamics. Given that, okay, let's try to find out answers to all of the other questions. Now, who started the dynamics? Why these dynamics? those are the questions that you cannot answer within the format unless the learning dynamics emerges from something else. So
no, but it's enough to say that there is activation dynamics. For if there is activation dynamics, then neurons find out that everything is changing, and then they start learning to model.
Why would they want to start learning, right? Because they have the ability to learn, because that's kind of built in their loss function. But you're right. You can have activation dynamics without learning dynamics. So no learning dynamics, just activation dynamics. In fact, all physics is built like this. There is no learning dynamics, just activation dynamics. And then can you from that produce something that where the learning dynamics emerges? Okay, that I don't know.
No, this is really the last question from your list for today. But I'm always trying to understand some basic thing about this weight matrix and bias vector, and I do not quite understand. They are unobservable, right? Everything we observe are basically fundamental neurons.
Right. Yes.
So this weight matrix is unobservable.
It can be directly or indirectly. So let me just explain you what I mean. So you may be observing the state vector, but indirectly that tells you information about the weight matrix and bias, and other way around. So what is exactly that you're observing is it can be either or, right? So by they're kind of related to one another. So if you are saying
yes, they're related, but the only thing, let's say, I can deduce really that there is a learning dynamics if I see that neuron is reacting in different.
I see. You
in
can
different ways to the same environment. So then I deduce that something changed. Weight changed.
Yeah, but you can also observe that something changed if you see that the entropy of the state vector is decreased, right? So you measure so you have no access to the weight matrix, you have no access to the bias. All you can observe is just a state vector of some one neuron, right? Just one number, and then you plot a distribution of that number, and then all of a sudden it acquires two peaks. x0, x1, and then those peaks become sharper and sharper. Now you have a distribution of that state, and then you look at it and say, oh, the entropy of this distribution goes down. Yes, I do not see where W is.
But as we discussed, it can be just a local fluctuation when the global all-encompassing weight matrix is stable, is constant.
Yeah, so that's why you have to, right. So you observe it for a very long time, okay, and you're saying, okay, well, looks like you observe for a very long time, you get one distribution. Then you observe for even longer time, distribution changes, and then again longer time, so different time scale, very long time scales, and then you see that during this 10 observations, the entropy decreases. So you're saying, aha, something internally changes, and you model it as, and you say, well, I model it as they're trainable variables. But you're absolutely right. What might happen is there are no trainable variables. It's just activation dynamics, and the learning dynamics emerges from it. It just looks like there is a learning dynamics. And if that's possible, then even learning emerges. Of course, all the attempts that were to try that didn't work, because you cannot really define well, you could try. I mean, I'm not saying this is no go. In fact, in dynamical systems where there is only activation dynamics, you can have like negative Lyapunov exponents, so the entropy is decreasing. So you potentially have even the learning dynamics emerge, but I just don't know how that.
But again, then it's just the one very long cycle. If it's
possible, yes, but maybe it's not possible. So I just don't know. I have no examples of a dynamical system with only activation dynamics where learning emerges, other than an example that I gave you where you have some.
But as well as I understand, it relates directly to the last question: are physical laws stable, or can the laws change of laws which is the last question in
Oh,
your.
okay.
It's exactly this question whether
I actually think this question was about more emergent level. So there are different level of emergences, right? So when we are talking about physical laws, we are usually talking about like classical and quantum physics laws, which in this framework are really emergent phenomena on much larger scales. And so can those laws change? And then yes, they can within the framework of the learning theory, because the particles can change their meaning, right? Quarks can change, the electrons can change, because they're all built out of the neurons, and then they may be sitting in the local minima, but then they may, fluctuate out of this minimum.
No, I understand, and this will be the direct evidence of learning dynamics. If we observe a change, it will be direct evidence that there is a learning dynamics.
Absolutely. Well, but for that you need to really observe change of. You have to test your system at the level of the fundamental neurons, right? Because like let's say you are seeing that one particle switch to another particle. Well, you're going to say it's not learning. I will just write a new term in the Hamiltonian that shows that this particle can change to that particle, and that's maybe and that's why when one way of interpreting that particle changed.
But if Planck constant changes, then
no, Planck constant, that's completely different. So Planck constant is if that changes, that of course is then the whole physics may change. I think before Planck constant changes, actually the standard model Lagrangian will change. So we have a Lagrangian that proved to work, and then all of a sudden you change its form. Now that would be very catastrophic, most likely, for all the chemistry we have, because chemistry relies on the standard model, and then probably we as observers wouldn't survive such a sudden transformation if it was truly new equilibrium. But something smoother than that, where you do not like have the entire chemistry change or entire standard model change, but you also only locally observe some high energy phenomena where you understand what the loss function of fundamental neurons, understand what the loss function of particles, and then you observe that optimization of this loss function actually leads to the changes in the behavior of fundamental particles. Yeah, that can potentially be observed without like killing everyone around.
But what are other possible changes which we can interpret as the learning dynamics directly?
Right. So there it's always UV or IR. In the UV we discuss right now. So on very small scales, you want to interpret, first of all particles as learning dynamics, understand what their loss function, understand what the small ingredients, and then study and see how at high energy scales the learning dynamics explains certain like high energy phenomena. Or you want to do it on the IR, in the general relativity scale, and you're saying, let's look at the behavior of dark matter. Well, nobody knows what dark matter is, or dark energy. Can that be explained as beneficial to learning, right? Would the dynamics of the large scale matter be predicted by the learning dynamics? Or because dark matter is a big mystery. We seem to see a lot of it in our cosmological experiments or observations, and yet we don't see any of those particles in our high energy experiments. So they seems to be present there in large scales, and they are not present in the small scales. So that is a mystery. But I think those are the two directions. So one is seeing how you can actually take a standard model Lagrangian, rewrite it as a learning theory, and then study why this form and not the other, and how we can show what kind of experiments we can suggest that will show that the particles actually learn. And the other one is large scales, trying to study the dark matter, dark energy maybe, and explain it through the learning. Yeah.
But do the particles do the particles learn in the sense that they demonstrate some learning dynamics, or we see just again the cycle in the activation dynamics?
That's the so you in learning dynamics tells you cannot have one without the other. So activation dynamics changes your state. Because it changes the state, there is some loss function constantly object. Now the question is not whether the two dynamics are present. I think they're both present, how non-perturbative they can be. So if the small system is stuck in the local equilibrium, it's kind of go through the same number of states, and you don't see now. All of a sudden, it starts to jump out of the state, so you see some non-perturbative phenomena. That's where you can catch it and say, look, the reason it did this is because it was learning. Okay, now you can say maybe the reason it did this because in your standard model Lagrangian, there was interaction term that allowed for this transformation. But that would be another explanation. And then you will see which explanation is better. Is it just better to write more fields in your standard model Lagrangian, or is it easier to just explain everything through the learning? So we don't know. We haven't seen that. But I think like in this learning dynamics approach, you always have two dynamics, right? Because if you had one, if you only had activation, really, it would really fast go to this high entropy state, and everything will just keep destroying. You will be in a heat bath, and we would be Boltzmann brains. And so I do think learning dynamics is always there, at least to keep things together, right? But then sometimes it does something non-perturbatively, where it goes from one equilibrium state to phase transition, right? We talked about this, and it kind of, this is what it is. You're sitting in one equilibrium, your loss function is pretty good, and then all of a sudden you go to another equilibrium. And then if that happens at if we can observe that happening on a microscopic scale, that would be a proof of the theory, of course. Yes.
So far, fundamental particles seem to all be in some minimum local, probably local.
That's right. That's right. However, there may be a degeneracy of local states. It may be jumping from one to, because there is always this interactions of particles that we interpreted. So they may be, but they are definitely very close to the true minima. Yes. Yes.
But on the other scale, we can say that like human person is not in any equilibrium.
It's not. And that's why I'm saying, yeah. And that's why I'm saying the best bet to actually test this theory is to go to very large scales, where things are very far from the equilibrium, right? The gravitational scales, or the scales of a person as well, right? So if we can have an experimental test of psychological phenomena, maybe next time we'll talk more about psychology, because those are maybe the scales that are easiest to test. They're easiest to test, but hardest to reproduce. That's the problem, right? So with any psychological experiments, you want to be able to reproduce it more than once. Have some setup where you can reproduce it, and that's the problem, obtaining it enough statistics. With a small scale system, you can reproduce it many times, but they're not much learning because they already learned everything they could. And so here you are stuck of choosing one or the other. Either you want to create more fine-grained experiments for the high energy physics, where you will study tiny jumps from one equilibrium to another, or you want to invest more into the study psychological systems, but trying to get your statistics under control.
Oh, it's really interesting, this thing about distributions and changing distributions. So that's a way to find out some criteria.
Right.
We can see many distributions about related to human civilization. We can find.
Well, those are noisy data. See, what past data are very noisy. Like if we can do now and take some subjects and study with some. We already kind of talked. Maybe it's a more subject for the next discussion of psychology. But if we can create a really clean experiments with people who are claiming to have some special contacts and special with the universal consciousness, if we can get those experiments under control with more statistics, perhaps that may be a useful way of testing the theory as well.
Now, again, this okay, so this will probably show the changes in the global connectome and the changes of the weights of the matrix. If we see,
that's right.
If we see the,
that's right. Okay. That's right. They will describe the change in the connections of the weight matrix exactly. Biases.
And another question, if we came to this to the weight matrix, is really what you are saying about search for the most beneficial local number of connections. If theoretically, if it is possible to be connected from one neuron to all the other neurons, it's I don't see why it is beneficial to have three-dimensional space. And
okay, so like infinitely many connections is bad because you just add a very large number of numbers, and all of those numbers keep changing. So there is no way any single neuron can predict the behavior of the sum of the states of all neurons.
If we believe for us, what I feel now is that really this world as a neural network theory is really bringing into the picture the huge number of hidden variables. All the weight matrix is just it's array of hidden variables, which is potentially much larger than hidden variables which are brought by many other by quantum mechanics. Yes,
I think it's not just the weight matrix. As we discussed, there are many neurons in this hidden space that may be rejoining our three-dimensional space. So it's even the state of neurons.
Yes, but even without them, as well as I understand, they are probably analogous to hidden variables of the classical quantum mechanics.
Yeah, exactly.
And weight matrix adds squared of new variables.
Absolutely.
Squared plus n.
But the only problem with it is not having it zero creates too much noise. Like, your activation dynamics becomes very, entropy in the activation dynamics grows much faster if you include a lot of connections. So, and then you cannot fight it, right? It's just constant inflow of entropy into the system. So if you really want to be able to fight the growth of the entropy due to the activation dynamics, then you really want to reduce this number. But yeah, in principle, every single neuron can be connected to every other single neuron. And if it is beneficial for learning, and in fact, this is what I call non-locality tests. Actually, maybe this is the best way of testing the theory, how we can enhance non-local connections. So people have non-local connections, but they are not claim to have non-local connections, but they're not really non-local in a sense of the speed of light, because if your connection is you're connected to somebody far away, but there's still the speed of connection is smaller than the speed of light, so then it's not really non-local. But if you can really enhance those connections somehow, create an environment where for the neuron will be beneficial to connect. So for example, let's say if neuron really wants to connect to at least one other neuron, and we, like, by construction disconnect it from everybody else, then he will have nothing to do but to connect to something else, right? Because he wants to learn. So if we can do that and then quickly reconnect to that neuron and then get the data from far away, that would be a proof of the theory, because of its desire to actually establish at least one connection, presumably more.
But even if we leave aside ability to connect to something far away, the local connectivity graph can be quite different. In 3D space, you can have many types of lattices, even regular lattices. You can have many types of three-dimensional regular lattices of connections, and it can be connected just to 6 nearest members in the cubic, or it can be connected to how many there are in the graphene structure. You can imagine any crystallographic structure and say that something, and if local connectome can change, remaining three-dimensional, then it becomes even more complicated.
Yeah, so that was studied in condensed matter, and actually all those effects only appear at the scale of the lattice. So that's why lattice field theories are so useful, is because it doesn't matter which lattice you use. It can be a square lattice, it's whatever, triangular lattice, whatever you want it to be. And if the differences only appear at the smallest scale, in the scale of the lattice. On the larger scales, there's no differences, and the spectrum of all of those spaces will be more or less the same. And that's why people are actually, there's some problems in physics we cannot solve exactly. And so what we do, we put it in the computer. How do we put it in the computer? We put it in the lattice. And it doesn't matter. We know it's not lattice. We know field theory is not lattice. It doesn't have like square-like structure. We still put it this way, do calculations, and then we can try for different lattice. There will be no difference at large scales. At the distance is much larger than the lattice spacing. There is no differences in calculations.
Are there similar results in neural network research, like that it's really at a local scale, the structure of connections is not important?
It's not important, right? So it doesn't have to be, it has to be, have three-dimensional. No, at the very small scales, the difference in lattices will appear, of course. So if you're able to probe distances in between neuron distances, if you can probe those, of course, it will all appear. But if you are only testing in scales that are much, much larger than the distance between nearby neurons, then it is harder to see that there is actually lattice-like structure. And again, this also goes to regular physics, right? So people are claiming that there is some discretization scale that has to be introduced, something like lattice-like, because without it, you get a whole bunch of divergences. But once people try to put those lattices, they see there's really no difference until you get to that small scale. And that people call a Planck scale, the scale where all those differences in the how you discretize your space will appear. And to test such small distances, you need to go to very high energies. And so that creates another potential problem of how to do that. Now, I also want to add that the non-local connections exist and can be prepared by creating entangled pairs, quantum entangled pairs. So in quantum mechanics, they would just be considered as two particles that are entangled, meaning that, and you can bring them far away, and then by measuring one, you're obtaining information about the other, but very certain type of information, and really more than just classical correlations. And so that's called EPR pairs. Now, in this neural network theory, they would actually be connected by the connection in the weight matrix, and as Victor said, it would be a hidden variable that actually connects them. And so changing one state really changes the other state, not because they're entangled, but because they're connected directly by the weight matrix.
No, just like some very non-diagonal element of the matrix is really right. Non-zero.
Right, that's right. No, the
but
diagonal.
Again, are there results which show that it can be beneficial in artificial neural networks?
Right. So having now, first of all, diagonal elements would not be good. If the weight matrix will be completely diagonal, that
no. I mean not near. No, the local connection means that everything near the diagonal is non-zero.
For 1D. For 2D, you necessarily have non-diagonal elements. But anyways, it's not important. Yeah. So studying what kind of spectrum of the weight matrix is beneficial and connecting the spectrum to the spectrum of certain graphs which resemble low-dimensional spaces is, of course, something that needs to be done that wasn't done. So like looking, which actually was done, but not with the respect of looking on the emergent space, right? So it is known that if you take a weight matrix, then certain spectral properties of the matrix beneficial to learning. It's also known that certain graphs with certain spectral properties resemble low-dimensional structures, 2, 3, 4-dimensional structures. Now, whether this spectrum and this spectrum have overlaps, and so really having this low-dimensional spectrum is beneficial or not, that's, of course, was not researched enough. Yes. Okay. Katya, are we done?
Yeah. Are we done?
Any let's say follow-up questions.
Yeah, about the loss function of the universe. Does anyone have?
Yes. So I think we answered in the way that for the fundamental one has something to do with information processing, right? So it has to do, like, the more information a given local neuron can obtain about the rest, the more beneficial it is. But then as you go to more larger emergent scales, we call it differently, right? On the biological scales, we call it's natural selection, we call it, right? Because or survival of the fittest. Well, and we talked about this. Do we survive so that we learn the most, and that would make sense, and then survival is just a byproduct of trying to learn the environment, or it's other way around, and you learn because you've survived, right? And so in the learning theory, you're saying that that surviving is just a byproduct. It's emergent property. The most important thing is to learn, but you can only learn if you manage to survive for longer time, right? But again, I mean, there's a question about UV wave loss function, meaning what is the fundamental loss function, and I think it's about information, at least in the unsupervised case. In the supervised, or better off, because it may be completely dominated by what this creator imposes on us, and then there is.
But can we really distinguish between loss function of a single human being and loss function of the species in a biological sense? What really biologists say about this?
Yeah.
So what's the loss function for the biological species?
Yeah, so we can create a boundary for any biological species, and for groups of biological species, and integrate over all neurons and figure out what is the total loss function of all of them. We can always do that, right? Whether it's useful or not depends on whether the system you've integrating over is weakly or not weakly coupled with the rest. So if you like divide myself, split on half, and left side is very much coupled to the right side, then I can still calculate the loss function of the left side and the loss function of the right side, but it would be not very useful concept.
But the question is whether we can find some simple form for this loss function
on the emergent level. Yes. No, not on the fundamental. On the fundamental level, I think there will be a simple form, and you don't have to. You wouldn't be looking at the humans. You would be looking on the more fundamental objects than chemistry or particles, and then you would have the answer there, right? But then once you coarse grain it more and more, and look at more and more and emergent systems, then this definition, well, integral is still there; it's the same. But it just has many more degrees of freedom, and so it's impossible to do this calculation. And you have to forget about something, and you have to coarse grain over certain things. And when you do that, then they'll just different and more useful emergent concepts emerge on different levels. And at the biological level, it's survival of fittest, okay, because it's more useful at that scale. It doesn't mean that the other things are not present, but it's just more useful concept. And on a psychological level, there may be something else.
But survival of the fittest is very generic, and there are many terms. Some of them drive to exploration. Some of them drive to
perfect. Yeah. Very good. So then the question is, can we do better than just call it with one term? Yeah, and then that's exactly what we try to do in this multi-level learning. Evolution as multi-level learning paper. Yes, we know that we want to survive, but that's trivial. Let's try to break and define a loss function of this learning system into pieces, and there will be a piece responsible. It is beneficial to be in the right environment, right? So then there's a term looking for the environment. It's a beneficial to be closer to food. So there is a term where you're looking for food. There is a term looking for maybe some partner, etc. Right? So you'll have all those terms added, and then once you model it, you look at it and you understand how much each term contributes and how much you can sacrifice one term given that the other term becoming bigger. And so yeah, absolutely, this is exactly what I call phenomenology of biology, right? Phenomenological approach, where you take real data and then you write all those biological terms, trying to, and for different organisms, it can be different things. You know, for us, like social experience is important. For other organisms, the social experience may be less needed. Things like that. Yeah.
Well, but you are saying that on the fundamental level, the loss function is maximizing information, and this is to decrease entropy. But this is just, this looks like just a main statement that evolution is learning.
That exactly.
But what about generally the entropy doesn't change in the universe, as I understand.
Well, it does. It does. It actually grows. So actually, we are always actually entropy grows, and so we are kind of losing the game, and we always get more information.
So that means that we are not good learners.
No, it means we were attempting to learn more and more. So, like when we measure entropy of the system, we're just looking at the visible entropy, what we have around us, right? And so it is not surprising. We should not be like taking one number and say what's the total entropy, goes up and down. This is irrelevant. We really have to look at the subsystem. How well are we performing? How well is this subsystem performing?
But
well
if we are talking about the subsystem, how can it's different from the loss function of the universe?
Well, there is an okay, good. So there is an overall loss function, which is the sum of the loss function of all subsystems. This is like integral. That's why I'm saying that integrate over the entire universe. You just take and add all of the loss functions of all of the subsystems, and you may also have.
But subsystems are on the emergent level. It's not
no. Subsystems like neurons. So like you sum over all neurons. So ask every single neurons, what's your loss function? What's your loss function? Average, right? And you
are they different?
The form of the loss function is the same, but the value is different. So you have like f of x, right? So f of x is the same, whatever f is. But x is different, so f of x is different. So the form of the function is the same, so everybody has the same task of learning the most. But some neurons are very successful in that already, and their loss function is.
But if we are talking about fundamental neurons,
yes,
these are basic units. How can we? There is no network, no weight matrix. How can?
There is. No. The fundamental. That's the whole point. This fundamental neurons are connected by the weight matrix. They're all connected to one another.
Yes, they are connected. So we can talk about the loss function or learning of some network. But how can we talk about?
Oh, I see. So take any network and then cut sub-network. Any sub-network will be a network with boundaries. And then you just think about, and that's what we are. So you are a sub-network. There are some connections. We
are on emergent level.
But you are an emergent level, but you are made out of fundamental particles. You are made out of fundamental neurons. So we can really draw you as a fundamental network with boundaries. And we can look at it. We'll look at the spectrum, as Victor said, and say, well, is this spectrum actually good? Are you a good learner or not? And yeah, absolutely. That can be.
But the classical.
Back to entropy of the universe. It looks like maybe I'm taking it wrong, but some parts are learning, some parts unlearning. So in general, there is no some general fundamental progress. Is it right?
Well, I wouldn't just call entropy. Entropy is correlated with learning, right? So the smaller the entropy is, the more you learn, but it's not directly related. Two quantities. It's like in thermodynamics, there is energy and there is entropy. Yes, they are related to one to another through temperature, but they're not the same thing. And so here, when we are saying what the network wants to do, it doesn't want to decrease entropy. Entropy is a byproduct of learning, but what it wants to do is to decrease the loss function. So
but the classical theory says that if some subsystem is very efficient learning, then somewhere outside it, entropy should be growing.
And that's fine. And that's fine. That's right. And that's
yes,
fine.
And so it's the place where my computers drop the heat.
That's right. Exactly.
So
exactly.
I cannot be effective learner without dropping heat somewhere.
Right. Exactly. Right. And that's what if you only include this three-dimensional space of neurons, there's nothing outside. Then it is true that you will in average entropy will grow, and only in the sub parts of it it will decrease. Now,
so what happens really with the fundamental neurons in these areas of universe where they unlearn, or they just lose the connections?
They unlearn, so they become kind of inefficient learners, right? So they lose connections, and they want to reestablish. They can start from scratch. It's like programmed death of neurons. You are no longer useful here. We throw you away. Go find better connections. And then actually that's what happens with humans, right? We die. We are not useful in this format. Yet we go and feed some other more primitive organism, and then become useful in that way. And so this is like recycling process of the useless neurons that would take in place. And that's useful algorithm. This is a useful algorithm.
So real danger is not in the thermal death of the universe. Real danger is when two efficient learning systems meet, their boundaries meet, and they find out that they cannot any longer throw away their heat.
Well, if the two systems meet and they're both efficient learners, they can do two things, like figure out whether they have orthogonal information, and if they have orthogonal information, they're useful to each other, and then combining together and throwing away all of the copied information. So if they have some information which is the same, they have to throw it away, and then they have information different, they want to keep it. So if that happens, then they form a more useful unit. But
they still need some outside. They still need some outside where entropy will grow. Once there is some outside of their combined boundary, then they can continue learning.
Well, it's a sum of boundaries, right? So minus intersectional boundaries. Yeah, of course. Mm-hmm. And then they figure out that by working together, just like two fundamental neurons, by working together, you can learn more, obtain more information than one of you, each of you individually. If both of you are recording the same information, then combining is not useful. But if you are recording different informations, then combining the efforts is useful. It's like when
but on the fundamental level, when two neurons cooperate, does it mean that somewhere nearby immediately starts some unlearning, some or not?
In a way that somebody nearby was predicting two separate neurons, and now all of a sudden they combine. So whoever was making a model of those neurons has to adjust their model, because that becomes wrong, right? So because they changed their state from being two separate neurons to combined neurons, whoever was predicting them now is making more mistakes than before. So its entropy of prediction went down. So has to relearn how those two systems
and then that's exactly this process when entropy
exactly
overall entropy is not decreasing.
Right yeah, but entropy is a really horrible measure of learning. First of all, the way we define
before you told that about how can we measure the increasing the amount of information, you are saying that it's the matrix is decreasing the entropy, or did I take it wrong?
No, it's a byproduct, right? So decreasing of entropy is a byproduct of learning. So so you start learning, therefore you should expect to see the decrease of the entropy. Okay, but it also depends on your temperature. So if your temperature is negative, then the opposite happens. So really you have to be careful there. But a general tendency, you see learning, entropy goes down. So by observing the entropy goes down, you can say, well, something is learning there. Right?
But so somewhere it goes up.
But somewhere it can also go up. But I'm saying there is no like universal law that will guarantee it to go up. So that's what I'm trying to say. There's no such thing as it is observed in the current state that usually happens, right? So entropy of the entire system usually goes up, but even that has counterexample. Sometimes you may have it's exponentially suppressed, but sometimes the system can decrease its entropy even through activation dynamics without learning. So just basing your judgments of how the overall entropy behaves, it's not interesting. Observing how subsystems behave, that's more interesting, because that gives you a much more amount of information about how.
But then we cannot talk about the universal, the loss function of the universe.
Why not?
It doesn't make sense.
Oh, no. So loss function of the universe is not entropy. Okay, it's amount of information that a given neuron processes on a fundamental level. So this is amount of information that some neuron is processing.
No, I'm not saying it is entropy. I mean that if it is related to entropy, so if entropy is growing, then what does it mean about the universe?
Right. So you can have a subsystem where the entropy is growing, right? And so like imagine yourself. You're right now very well understands about your environment. You know what's happening. You live in the same city for a long time, and then you know how to predict it. Now all of a sudden you are moved to some foreign country. Now you have no idea what's going on around. Of course, your entropy will grow. Entropy of how you perceive the environment will grow. Okay, and now you'll start learning that again, right? So and then eventually your system, your entropy will go down. You'll be able to predict how the environment will behave, and that will be an indication that you are learning. Now, but you can say, all right, let's look at the whole. From the very beginning till the end, what happened? Entropy didn't change, or maybe it even grew because you didn't spend in a foreign country long enough time. Well, but it doesn't mean that there was no learning. There was still learning. It's just your environment is more complex, became much more complex than it was before, because now you're changing your environment. And the same happens here when the certain system increase their entropies, because it is end up in the environment which is more which is not like it used to be, right? So environment changed, so entropy went up.
Yeah, for some subsystem, environment can change, but if we are talking about the universe,
and that's what I'm saying. This is just one number, and it's not very useful. From what we observe, if we are integrating over only this three-dimensional physical space, yes, we observe that overall entropy grows. But this is just one number. It is not a number that will tell you exactly, how this entire neural network will behave, because there is, all those n-squared connections that Victor was talking about, and all those hidden neurons that we were talking about before. So this is just a number that we can naively calculate, and it does show that the entropy of the universe, at least in the three-dimensional sense, is growing. However, I will add to this one more correction. That's not how gravitational systems behave. So if you look how gravitational systems behave, they actually, you start with a dust of particles that spread out through the universe. And if forget about expansion, right? So particles start collapsing, right? So they try to form clumps, form galaxies, form stars, right? So they lose this positional entropy, and all attracted to some points where the entropy is lower. So if you really think about, forget about general relativity, just Newtonian mechanics, right? Then you will see that the entropy in this gravitational system seems to be growing. It's decreasing. So it's not as simple as just saying, yes, the space grows, and so the entropy will grow. There are more ingredients to this. And one ingredient is, as I said, gravitation. The other ingredient is, observers, like we discussed, and they seem to be always fighting this increase of the entropy by learning more and more about the environment.
Yeah, then I will repeat again my previous question. If we are saying that the loss function of the universe is related to growing amount of information.
No, we said the fundamental loss function. It was a conjecture. It's not a claim, right? So the right thing to do. Let's first say. I'll repeat what the right thing to do. We have a standard model Lagrangian. First, we write it as a learning theory. We figure out what is the loss function of all of the particles. Then we keep doing it until we figure out what the fundamental neurons are and what is the loss function that gives rise to the emergence of particles, molecules, cells, etc. Once we figure out that, we'll know an answer for sure what it is. Okay, so let's put it aside. This is the right way of doing things. Now let's do the wrong way. Okay, let's say we're just starting with the neural network, and then we want this to have a non-trivial dynamics. What should the loss function be? And let's assume it's unsupervised, so there is no boundary, nothing. And then you say, okay, well, let's start with a simple thing. Let's each neuron have a tendency to minimize its entropy. It's just it's a conjecture, right? It's not a proof. What if? Okay, so we are starting with this. Then we know what will happen with the probability distribution of the states of neurons. They would want to be more narrow and narrow. So this, if you have a spread distribution, the entropy is high. If you have a small distribution with small variances, then entropy is lower. So that's what they want to do. So for example, if you have a neuron that do classifications, that will have a peak around 0 and peak around 1, or +1 and -1. And if each of them collects the data and moves its weights so that the information becomes smaller and smaller, if that happens, then what you will get, you will have some kind of dynamics. And then we can say, will this dynamics produce three-dimensional space, or the other stuff? We argued today that, and before as well, that it would not be beneficial for such neurons to be connected to every other neuron. That would not be beneficial. It would also not be beneficial to such neuron to be disconnected from all neurons. It would be because this way you'll get zero information. And so if that's the tendency, then what you will end up doing is having some small number of connections. I don't know if it's going to be 2, 3, is it going to be forming a local three-dimensional space or not? And then we discussed that really what one has to do is to look at the spectrum of efficient weight matrices, right? Doing efficient learning and machine learning, and then compare them with a spectrum of graphs that you would get in a three-dimensional emergent spaces. And then if there is some correlation between them, then we can maybe study and understand what kind of features of the learning dynamics or what kind of elements in the loss function actually do give rise to this three-dimensional emergence. This was not done, but that's kind of the directions I would have to follow.
Okay.
I don't know.
Yes.
Oh, Meryl, how are you?
Yes.
Nice seeing you.
Hey, good to see you. I
you.
came on board this. I didn't know you were hosting something or not about the great discovery today. I just can't believe. Remember, you and I probably worked on this 4 years ago on the cosmic web.
Maybe, yeah.
I mean, I don't know, maybe it was longer, 4 or 5.
Right. Could have been. Yes.
And so we were comparing it to the brain, and I also had a Caltech guy, Edon Ginsberg, who we finally ended up writing a paper back then. But
I remember. Yeah. It was after I published that article. It must be 3 years ago. Yeah.
Right. So anyway, I just woke up to this wonderful news about
You should be joining us every week. I mean, and
what's the name of the group?
It's the World as a Neural Network group, and we meet every week at noon Eastern time. So we're almost done now, but you're welcome to. And we discuss all the crazy questions from quantum mechanics, cosmology, psychology, biology, you name it. We have no idea what we are talking about. We are still trying to figure it out, and so.
But aren't you excited though about the fact that they've finally discovered, we knew that there were filaments, but now we know what's inside them and all that.
Well, there's more work to be done with the filamentary structure and how they're related to learning, but I'm on it. I can tell you for sure.
Yeah,
Now,
that's great. We'll keep.
I was excited about
connect.
filamentary structure when I wanted to write it dynamics, and I tried it like 6 or 7 years ago as a field theory, but it turned out to be more complicated than that. And so, and that's why I do think it is learning dynamics. Yet work needs to be done to actually show that that is the way.
So it's a working dynamics, you said?
Learning dynamics. No. When I'm saying that, like, the standard approach of the physicist, you show any pictures or something random, and the physicist will say, okay, well, let's describe it as particles or fields, because those are the only two things we know. And with the filaments, they are simulated as particles, if you, but they are not. And you can try to describe them as fields, but they're not. And so you run out of ideas eventually. But I think it may be possible to describe it as a learning dynamics of a neural network that is just makes grows synapses, makes connections stronger, and that actually is related to the question why 3D is more useful, right, than any other dimensions, because it is only in 3D that the strings or filaments intersect non-trivial. Like in 2D, the strings they're touching each other, and there is not much interest. In 4D, the strings or filaments, they'll miss each other. They will never intersect, and nothing smart will form
because it moves with time or whatever.
Yeah. But in 3D, this is exactly the right dimensionality for the two strings to actually intersect. And that's why I'm thinking that it is related to the filamentary. So the study of filamentary structures and the showing how the dynamics of large-scale structures can be mapped to the dynamics of neural networks. I think if that can be shown and say, okay, here is a neural network, its dynamics resembles dynamics of filamentary structure. It's a different description of the same dynamics, and yet it is completely just learning. And if we can do that, I think that would be very useful. I
got a funny one for you. So here I am on your podcast, whatever
meeting,
this is.
group meeting.
Group meeting, and I just suffered another major blow to the head.
Oh no.
I know. So I'm one of your. The minute I get a chance to relax, which I'm doing now, I go right to the cosmic web, which is right up in here, and
it's the same.
Anyway,
maybe the same.
God. It's unbelievable.
It's also now bringing together, like we are studying cosmology now, but the reason why 3D is useful may also be for how our biological neural networks learn. Again, having being able to have this three-dimensional connectivity, maybe okay, there we go. So it may also be related. But again, all these things were not modeled. So what needs to be done is to write down.
Did you see what I'm holding up?
Yes, I do see that. Yes.
This is
so what needs to be done
is my reading.
Actually, have a simulation of the large-scale structure with all the complicated filamentary structure. Have a simulation of the learning dynamics with the well-defined the dynamics of weights and show that the two are actually equivalent. And then do the same with the biological networks. And then it may be the same, may be different, right? So biological networks may have a different dynamics, and then figure out what is the loss function that is driving that dynamics. Is it the local? Is it like would be for unsupervised learning, like what I call a bulk loss function, or is it a boundary loss function? Is it supervised learning? So all those things can be answered with a simulating and modeling both cosmic web and biological network. Yeah, that's a good point.
What about the concept of consciousness?
Okay, Katya, are we going to discuss it at some point in the later meetings? Consciousness.
Sure. Yes, at some point.
Okay, Katya is the boss. So if you have questions,
maybe we should mention that there are the records on YouTube of the previous meetings, and we have already had some discussions on that, and maybe you can check.
Absolutely.
And of course, I think we will have some more discussion.
Definitely, consciousness, free will, all those things. I mean, they just it's impossible to cover everything.
Next time we are planning kind of related questions, I think.
So for next time, was it biology and psychology, right?
Yes.
Yes. Okay, very good. So yeah, Meryl, you should join us next time as well.
Definitely. Can you give me the information how to get online? I don't know how I found this, but
okay. How did you find information on Facebook or on Telegram? Where?
Oh, you're on Telegram. Okay, so that's well.
No, as well as on Facebook. Are you on Facebook, right?
I have Facebook. Yes.
Okay, I'll send you a link.
Okay, that'd be great.
But it's the same link each week. It's same link.
Yeah, it's the same link. This link you found.
This the one you use now.
I don't know how I found it.
All right. So
okay,
and then next but we are meeting 2 hours earlier. So we're meeting at noon Eastern time.
Noon Eastern. So it's 9 o'clock for me in California.
So get your coffee earlier and then.
Oh no, I don't. Oh, I get my coffee at 6 in the morning. So.
All right. Okay, Katya.
Yes, we are running out of time, and we don't have time to discuss the third question. So we will skip or we'll postpone it to
till next time.
Another meeting. But we already touched the fourth question. So maybe we check if we are done with it. Let me read it.
Well, we're running out of time, Katya. If we are not done, we wouldn't have time to finish it. But
just send me
let's
what you
check
want to
if we finished it or not. I suggest.
Sure.
Yeah. Okay. So in an evolutionary universe, we shouldn't. Why shouldn't the laws evolve? Or other way, in an evolutionary universe, how the laws of physics can be conservative?
Right. So I think the answer to this question that if you really model universe as a neural network, then the fundamental law that you define as through learning and activation dynamics should not evolve, should be just given once and for all. However, all of the laws that emerge from it on a more microscopic level are free to evolve and change. And we discussed that. You're absolutely right. And it would many changes may be catastrophic and too sudden, right? Suddenly change chemistry of our local universe may be disastrous to everybody, right? But having small perturbative changes may be just reabsorbed and reinterpreted as some fields or in the standard model, and so maybe they're just expected small changes. Sudden changes is something you would not expect. But to answer the question again, to summarize, the fundamental laws are assumed not to change, so it's like an assumption, maybe wrong or not, and that's the law in dynamics. Everything on the emergent level, everything on the level of physics, everything on the level of chemistry, biology, psychology, all those dynamical, all those laws, if we have them, they can change. So of course, we do have very good laws that describe how things behave on the level of physics and chemistry, less so in biology, but we also discuss today how one can phenomenologically model the loss function of a biological system, and therefore observe how this loss function changes with time, and that would be okay. That will be completely consistent. They would be changing, and we'll be observing them. Yeah. So I think we've pretty much covered it a few times, but again, I mean, this is something that we'll be coming back to often, which is okay, right? Yes. Okay.
Okay.
All right. Thanks.
Well,
Then
were you
I'll
excited
stop
about the
recording.
announcement? Were you excited about the announcement?